In the previous session, we saw that we can give the model some freedom to decide how to represent intermediate features in a multi-layer networks. So, for example, when we dealt with MNIST dataset to recognize handwritten digits, we told the model you have a freedom to choose any 30, like you can have 30 features. 30 ways to represent those digits, and then you need to take those 30 and shrink them down to the 10 labels that we want you to do. And we didn't tell the model how exactly those 30 should be represented. It was up to the model to do that. Now, so far we've been dealing with only numeric inputs. For example, in this input problem, we had the numerical inputs as pixels. So each input was either 0 for the black or 1 for the white dot, and I think there are also grayscale. So there can be intermediate values between 0 and 1. But then a lot of modern models, they deal with text. So how do we represent text? How do you convert strings to numbers? One way of doing it is to building a vocabulary. So you build like a big dictionary of all the words in your vocabulary, and you just assign index to the words, right? So you, for example, you have input string fish eat food, and those are the indices of the corresponding words in your dictionary. Those don't have to be full words. It can be subword units. We call them tokens. This is a very common word that you hear today with LLMs. So instead of grabbing full words and putting them as a standalone entity in our vocabulary, we can have subword tokens. And those vocabularies can be quite large. Let's say that we build a vocabulary of only 10,000 English words. It's still a very large vocabulary. And then we say, okay, we give them numbers, but those numbers are not very good for using them directly in machine learning. The problem with them is that, the world at position 753 is not close to the world in position 754 or 752. So just because they happen to be, close together numerically by index in your vocabulary doesn't mean that those words actually have similar meaning. And that would confuse your machine learning system. We need to come up with a better way to represent, to convert strings to something that the model can understand. And the trick is first, let's see, we will just use one hot vector. So each word will have a unique index in our one hot vector. So if I have a vocabulary of 10,000 words, this is my vocabulary, and each word has its own index. I will create, for each word, I will just create a one hot vector, just like we did before with 10 digits here, right? So with 10 digits, we had 9 zeros and a single one. In a vocabulary with 10,000 words, we'll have 9,999 zeros and a single one somewhere at the position where the word index is. This can be, this can look quite silly to represent it this way, but we'll just go with this for now. So let's say I did this, and then I would take and do a matmul with the first layer of my model, where I would have 10,000 rows and 200 outputs. So for each input, we will get like 10,000 words, and we compress it to just 200 features. And then my model can shrink it further, like going to 30 features and further. And like, we saw how in the previous example, we went from, input pixels of 784 to just 30 features, and then from 30 to 10 digits predictions that we did, right? So this is something similar that I'm doing here. But first I'm going like to 200 features. Now, this is not quite like we do it in real life, because this matrix is quite large, and as the vocabulary becomes bigger and bigger, it will get even larger. So we just don't want to waste our resources so doing this huge matrix multiply. And in reality, if you look, when you multiply by 0, the output is 0. So what really happens with one-hot vectors when you multiply them by a matrix like this, you simply, like the result of taking a vector like one-hot vector and multiplying by a huge matrix like this, the output is just the corresponding row. Like, let's say fish was 753. So after you multiply this vector by this matrix, the output will be simply the 753rd row of this matrix. So it will be like 200 numbers, right? Because we output in 200 things. That's simply stored in the 753rd row. And it doesn't matter what the values in other rows, because they all get multiplied by zeros. And then we say, okay, why would we perform this silly matmul? It's very expensive. Instead, we'll just do a lookup into this table. It's much cheaper. So what we really do is something that we call embedding lookup. We take this table, right, this matrix, and we say, I want you to return row 753, 1345, and 453. And it will simply perform lookups. A lookup operation is something that computers are very good at. It's a very cheap operation. And then you feed it to your other layers, whatnot. Like the architecture of the model can be, whatever you want it to be. And then when the gradients come back, you need to update your parameters in this model. You simply update those corresponding rows with those gradients that come back. You don't touch any rows that you didn't touch. So this is how the modern models work, and we call this embeddings. It's just to avoid doing this very silly one-hot matmul. Now, when we look at this table, this embedding table, after we trained our model, you can see that the model actually gives some meaning to these words that it's training on. Specifically, a well-trained model will have, if let's say I put here 200, it will be vectors of 200, and then you can try to cluster. You can say like, okay, let's see, let's find the word fish, for example, 753. And then you can look for similar vectors, the vectors that look the same. And you will see that those vectors that's somewhat similar to the word that you're looking for, these are actually related words. And there was a famous paper that showed that they trained a model with embedding tables, and then they showed that if you take the trained embedding for word king and you subtract man, you will get something that's similar to queen minus woman, or king minus queen would be approximately equal to man minus woman, or Paris minus France would be plus Poland would be something like Warsaw. So this vector here would be approximately similar to this vector there. So although we cannot understand the meaning of these 200 features that the model assigns to each word, they have a meaning to the model. And if I retrain the model from scratch, so I will randomly initialize this whole thing, with different parameters, the vectors that I will train after training from scratch will be completely different. So but they still will have something like this. They will still have this meaning preserved. And the interesting thing is that it's not like we're just bucketing all words into 200 features. There are actually a lot more things that the model can do, and it has to do with with the fact that we're using very large dimension here. Like in some models, this would be like up to 4,000 maybe features. So it has to do with the fact that in multi-dimensional spaces, like when this dimensionality is high, we can pack a lot more information into those vectors. Like how many orthogonal vectors exist in a d-dimensional space? Exactly d orthogonal vectors. So those orthogonal vectors means like vectors that 90 degrees with each other. So obviously, if you have like a three-dimensional space, for example, in three-dimensional space, you can have only three vectors that have 90 degrees. But when you go to large dimensionality, like 200 or maybe 1,000 dimensions, then you can create many more than, like let's say our dimensionality is 200, I can create many more than 200 almost orthogonal vectors. So vectors that are not 90 degrees apart, but maybe somewhere between 88 and 92 degrees apart. There will be a lot more vectors like that almost orthogonal. And that means that I can pack a lot more different features into smaller, I can compress more features into smaller, dimensions. And that's why our models, they can store a lot of information about words when we use embedding tables. Another thing I should mention is that the dot product operation that we have been doing, it has this mathematical property that if two vectors are orthogonal, so the 90 degrees to each other, then the dot product between them would be 0. Because another definition of a dot product is like this: the length of vector A by the times length of vector B times cosine of the angle between them, between those like vectors A and B. And if vectors A and B align, like they point in the same direction, then the dot product between them will be the highest, because cosine is the highest. And if they point in the opposite direction, it will be like some negative number. So it is often useful to also have your embedding table. So let's say I have a model that wants to predict the next word, like LLMs do. But this is a much more simplistic model. I will have 2 words as an input that goes through embedding table. We look up these words. We then perform some kind of multi-layer perceptron. And then I have this multi-layer perceptron will output me a vector of 200 numbers, right? It's some kind of, that has a meaning. And one thing that I can do is then I want to look up which of the vectors in my embedding tables, in my embedding table, I want to find the vector that is the closest to the vector that my model output, so that I can return that word. And the way to do it is just to transpose the embedding table, just like turn it on the side and do a matrix multiplication with it. Because the dot product is looking for, like, it returns the highest value when the vectors align the best. So essentially, by doing this matrix multiplication, we're finding like the highest value returned will be the value that that corresponds to the word that's the closest to the one that our model output. So then we can do softmax. Softmax again does the normalization and shows us as probabilities. So then after softmax, of all these 10,000 candidates that it showed, that it returned, we'll find the one that's maximum, and it will be a word that will just return, right? So it will give us like which word is the closest that our model predicted. So that's this is not how the real LLMs work, but this is a nice trick of storing textual information and then also looking up, doing the reverse lookup. I hope you enjoyed it so far, and we might see you in the next session.